Good afternoon, and thank you for joining me today for this webinar on SOLIDWORKS Flow Simulation, and specifically the free surface capability introduced in SOLIDWORKS 2018 and also 2019. Today's look will be a little more specific, a little deeper dive into how to use free surface, what it does, and so it's really intended for users of flow simulation, maybe a bit more of an advanced look, but if you haven't seen it before, this is a good place to be as well. Let me introduce myself. My name is Philip Morrow. I am one of the simulation specialists on staff here. I'm an applications expert with MLC CAD systems. I've been here a little over 5 years. You might see my voice around on some other YouTube videos concerning sim or flow simulation, or if you're calling for tech support, you can get a hold of me directly over these topics as well. So I don't want to spend much time today talking about myself, who I am, or who MLC is. I hope you know by now. Let's jump straight in to what we're going to cover today. So the first thing I want to talk about is what is free surface? What is this immiscible fluid capability that's been added? What kind of examples is it used for? And what can we do with it? Then I'm going to jump straight into a how-to and go into the specifics of what I would do to set any of these simulations up, and some things to watch out for, and great ways to post-process. I'm going to do this as a 2D example, and I'll actually solve one here in real time. So we'll go start to finish, not skipping any steps at all. Of course, these are not just for 2D simulations. It just makes it nice today for the webinar. So I want to show you some 3D examples as well. So jumping right in, what is free surface? So this was introduced in SOLIDWORKS 2018, becomes more capable every year. So anyone using 2018 or 2019 flow simulation will have this capability. There's no advanced licensing needed for it, simply this version, this year of software. And what free surface allows you to do is simulate flows with a freely moving interface between two immiscible fluids. And that just means two fluids that cannot be combined easy, so air and water, right? Or oil and water, something like that. This uses the VOF, or the volume of fluid technique that's really used by everything you do in SOLIDWORKS Flow Simulation. This means that we wouldn't do something where we aerate water into air, like spraying out of a hose, but we solve this with a single set of momentum equations and track the volume fraction of each of the fluids. These are going to be transient or time-dependent studies. So I mentioned I'm doing this in 2D. When you get into fluid simulations, solve time can take a bit longer. Now, FlowSim will use all of the computer you give it. So if you're hyper-threading, you got multiple CPUs, it will certainly use all that. But keep in mind, transient studies, or studies that take place over time, can take a little longer to solve and be a little bit more computationally intensive than your general steady-state setups. This is also available for gas to liquid or liquid to liquid fluid pairs only. Luckily, that's about everything we work with, but you couldn't do here your non-Newtonian fluids, or say you were going to work with a real gas model or steam. In this case, just gas liquid or liquid to liquid immiscible fluid interfaces. What's not allowed is, of course, phase change. But some of those advanced options you might turn on as well, like rotation, if you're going to use a porous media, perhaps to represent a filter. We couldn't do that. We couldn't run fan models, or maybe humidity or cavitation models also wouldn't be turned on in this type of setup. So let's talk about a few examples. There's a lot of times you might see this. One of the most basic ones would be filling time and fluid behavior of maybe an empty tank that you're filling up, or a tank that's starting off partially filled. It really doesn't matter about the starting condition or starting situation. This is a nice one in 3D. We could also do something like this in 2D. Yes, we could calculate tank fill times ourselves by hand, but we don't need to if we've got a computer like this in front of us. So we could set something up to fill multiple tanks and understand that mixing behavior between multiple fluids, or just tank fill time. So I hope that gives you a really quick idea of what free surface is and how it's used. Let's dive in, like I said, to something a little more specific, where I might show some of the advanced controls that you don't see all the time when you're looking at YouTube videos of free surface examples. So to do this, I'll start off with a 2D simulation. And the one I've brought today, I think is pretty interesting. This is a flow problem of a dam breaking. You know, I'm from Austin, Texas. We had a lot of water this year. We usually do around October. All of our dams had their floodgates opened. And this kind of caught my eye. In this case, I'm going to model water in one area of a tank, air everywhere else, and I'm going to start a simulation at the moment that a wall is removed from holding back this water. So the exact moment a dam would burst or not be there anymore. As this moves over time, of course, we're going to get the water spilling through where it used to be held back by the dam wall, but since this is also inside of a tank, I want to see what it looks like when the water travels all the way to the other side, hits the wall, and produces a bounce back wave towards the initial stage side of my tank. So let's jump straight over to SOLIDWORKS. Let's look at some software. Now what I've got modeled is something very simple. I basically just have two bodies here. What you can see is a rectangular tank wall around the perimeter, and then I've got another body here that's going to represent the water in its initial state as it's held back by the dam wall. When I start off a flow sim, no matter if it's the first one I'm doing or something very advanced, I go through the wizard. Now this wizard is going to set up everything we need for the project. It's going to help us with the meshing parameters and also with parameters in the solver. So I wouldn't skip it unless you've got a template set ahead of time. I wouldn't go straight to new project. I would always use the wizard here. And let's call this a dam break. I'm going to use the current configuration. These projects are configuration specific, but in this case I've just got one configuration called default. And then I'm prompted to set my system of units. Since I'm working with some standard SOLIDWORKS stuff, I'm just going to use the SI units. But I want to point out, you can find just about any unit you want in these drop-down lists below, or make your own custom units. And there's a really large area of units to choose from. You can come back here, but I would say set the units exactly like you need them, and then just create a new system of units so you only ever have to do that one time. Now for today, I'll just use the SI system of units. Now you might have noticed in my geometry, I've got a wall, the tank wall, all the way around, but on two sides of this, I really don't have anything at all. So I'm going to set this up as an external analysis just because I don't have CAD geometry that completely seals off an internal environment. External analysis here, they're basically internal and external at the same time. I don't have any cavities with flow conditions I need to exclude. I don't need to exclude any internal space. So now let's turn on the actual equations and things used by the solver. Now if you turn on free surface, it's going to prompt you to make this a time-dependent study. So like I mentioned before, all free surfaces are transient analysis. And I'm going to keep the time kind of simple. I just want to look at, let's say, a second and a half. So do 1.5 seconds. But I'm not really going to mess with the output time step here, or how often I'm saving results. I'll come back to that and show you the real advanced controls for something like that. I do need gravity turned on, and I'll just check the arrow in the graphics environment to make sure it's going the right direction. That's what's going to move this water. And then I'm just going to turn on free surface. You might have noticed when I did that, the option to use any rotation methods just went away. So that's not possible here. But you can turn on heat conduction, radiation, calculate convection. That's all still available. Advancing to the next screen is where I get my default fluids. What I'm going to start with fluids. And notice the default fluid type says immiscible mixture. And this is because of the free surface setup. So in this case, I'll just add a gas. I'll double click air to add that to the project. And for my liquid, I'm going to double click water. Remember, for free surface, you have to choose between gas and liquid. If you do get down into steam or non-Newtonian liquids, it's not going to allow that. For my starting condition, I'm going to use air and water as my default fluids. So initially, until I tell it otherwise, everything is going to be filled with both. And of course, I don't know if it's laminar or turbulent, so I'll let the software figure that out for me. Your initial wall conditions and your initial starting conditions can stay at default values almost all the time. Adiabatic wall that has zero roughness to it for no slip of the wall conditions are pretty straightforward. And in the final initial and ambient conditions, I'm just going to leave this. Nothing's moving to start out with. We're at standard 1 atmosphere of pressure and temperature. And you might take a look at your substance concentrations here. Whenever you're adding multiple fluids to a project, you can decide what your initial fluid is. In this case, I'll say everything is initially air, and I'll just hit finish. Now, when I hit finish here, Flow Simulation actually created me a tree that I can work from top to bottom on, and it created a computational domain that is this large cube you see on the screen in front of you. In this case, that's way too big. Usually an external analysis might be for something like an aircraft wing. So I'm going to start at the top of the tree and just edit this computational domain and shrink it down to the size I need. You can interact with these handles right on the screen, but I'm going to interact with the property manager and set up a 2D simulation, and this is going to be symmetric about the XY plane. So this automatically set my Z directions to symmetric boundary conditions. Again, you can drag on the screen. I actually know some numbers here that are going to work out nice because I know the limits of my model. So I'll just enter those and shrink this down to a much smaller size just to the tank that I want to work with. There you go. That looks pretty good to me. You can see the dash border of my computational domain. You can hide that stuff from view if you don't want to see it all the time. Now, I do need a couple of boundary conditions here as well. There's actually no top on this tank. That's where air would be. So boundary conditions are normally my ins and outs of a project. In this case, probably there's not too much coming in or out here. It's really gravity that's going to move everything. But since I've got the sky above this, I don't really have a top on this tank. I'm just going to say the top face here that would represent where we'd be open to the air. I'm going to represent that as a pressure opening to environmental pressure. And everything below here is just going to take the defaults that came from that initial wizard. So standard atmosphere and pressure. My substance initially there is air. So all I need to do is choose the face and hit the green check. Pretty easy. Now let's get a little bit more advanced. One thing is the mesh. The global mesh here works pretty good for most projects. I usually leave it on 3, maybe enter a minimum gap size. In this case, I just want to make sure we have enough mesh cells here to get some decent results. So I'm going to switch from the automatic settings to the manual. And notice the basic mesh. This is how many cells we start with before we start dividing up into more. If I show it to you now, I've got 8 in the X direction and 6 in the Y. There's no hard and fast rules here. I'm just going to make sure we get quite a few more starting cells. Perhaps something like that looks pretty good. And that's all I'm changing for the starting position, starting characteristics of the mesh. That should be enough for what we need today. Let's get a little deeper, though, into these initial conditions and setups. So this gets a little bit advanced. I want to show you a technique called initial conditions. I'm actually searching this in the command search up in the top right. If you ever wanted to know where it lived, though, you can, when you're searching commands, hit the eyeball there to find out where things are. They're also in the Flow Sim Command Manager, but I like just using them right out of here or dragging them from this drop-down onto a toolbar that you use regularly. What an initial condition allows me to do is just have a different start. So you might notice I have a rectangular body here that represents the starting body of water. What I'll do is I'll choose that body. So this is my water domain body. I'm going to say all of that. And because I made a solid body there, I'm going to check the box that says disable solid components. So now it's not a solid body anymore. It's whatever I tell it is. In this case, it's water. So that's it. Initially, this volume right here is all water. And I'll hit the green check. Now what that did for me was it left this body here for that definition. But if I actually right-click input data and take a look at component control, it has disabled that body. That's what turning it off did. So now that body won't block the flow like a solid. It'll just be what defines water as my initial starting condition. Let's go a little bit deeper as well. What I want to do is control the time step. I said I was going to do a 1.5 second solve. So just like where I found component control, I'm going to right click on the input data folder and open up the calculation control options. These options are definitely advanced, not everybody sees them, but you can see my physical time here is set to 1.5 seconds, so that's my total time. Well, how often am I splitting that thing up? Over on the solving tab, for most transient studies, you can use the automatic time stepper. That's a great way to go. If things are going easy, it'll use a big time step. If things are more complicated, it'll lower that down. It'll give you the best solve time right out of the box. I want to look at specific time steps in between here, so I'm going to set that to manual, and I'm just going to take a time step of 0.005 seconds. Now, if you set this to manual, the other thing to wonder is how often are we saving these results? You might not want to fill up a hard drive. You save every time step there. Normally, this is controlled as well, and you can set on the saving tab how often you're saving out full results to do things like make animations with later on. And I want to show you here something that was added in SOLIDWORKS 2017. This works for any transient analysis from SOLIDWORKS 2017 or after, and that's the Transient Explorer. So instead of having to make my results and then jump into an animation suite, I can turn on this Transient Explorer. It just helps with post-processing later on. It has some automatic parameters down here that it's saving, and I'm just going to look into those. I want to also look at mass fraction of water and volume fraction of water, maybe immiscible water. These are all things that I just want to be able to play in animations easily later without having to take any extra steps. So these calculation controls, they're where you can tell how's the solver know when it's done solving, in this case 1.5 seconds of physical time. What time steps is it taking? Very nice for thinking about animations later. And then how often are we saving these results, to think about the amount of hard drive space we're using, and the Transient Explorer just to make animations nice and easy. And I'm going to hit OK. At this point, I'm actually ready to run this study, which I'm going to do. But I want to point out one more thing for you. I'm doing a very qualitative analysis here. I want to see this wave break down from having no dam wall and then bounce back from the other side of the tank. But you really should set up goals anytime you're running a flow simulation. Goals are those hard numbers that you care about. There's always good goals behind the scenes used for convergence control so the solver knows when it's done and it's being accurate. But if there's a number that you want to plot, maybe it's density somewhere, maybe it's a final volume fraction, insert a goal as points, surfaces, or global goals. I think today, though, I'm just going to run this. I'm going to hit run. I'm going to do this in real time so you guys can see. So the solver is going to have to mesh, and it's also going to solve this. It's a brand new calculation, and I'm just going to hit run. When you're running these, you can choose how many CPUs. I'm using all of my 4 CPUs here, and it started calculating right away, and I'm just going to pause this. Now, this is monitoring a solve, something you don't see too often. When a solve runs, I mentioned these transient analysis could take a good bit of time. You actually get real-time feedback when something is solving. So you can see how many mesh cells are used, where are you in the physical clock. You can see if there's any warnings that pop up. And something I like to do, and this is only available during a solution, is to insert a preview window, which is simply a cut plot. In this case, a cut plot I could look at on the front plane, and let's look at mass fraction of water, and a plot will be generated that when I unpause and continue solving, you can actually see how things are behaving. And this is great. If you have a longer solve time, you'll know if things are headed the right direction or if something's different than you expected. You could stop this, make changes in your flow simulation tree, and then just restart it, and it'll pick it up right where it left off. So don't worry too much about solve time. You do get this in real time. You can also, if you right-click any of these and jump back into the properties of this plot, change what plot you're looking at or save every image in this plot so you can play these as an animation or as a movie. In this case, things look like they worked out pretty good. I saw my wave travel across the tank. Looks like it's hit the wall on the other side, and now I'm getting a bounce back wave all the way over to the start. So that's what I was hoping to see here. Now we are just about 1.5 seconds of real time. So when I got there, I see the solver is finished, calculation is finished. At this point, I can just close the solver window and get back into flow simulation. In my tree down at the bottom, you'll see the results are automatically loaded for the last time step, and you can expand these to start making plots. If you want to see a specific time step, just right-click on the results folder and hit load time moment. And any time moment you saved, which I just saved first and last there, you can load that specific time. What I'm going to do in this case, though, is turn on the Transient Explorer. That's what I enabled inside of Calculation Control. And you can get to this just right-clicking on your results folder and choose Transient Explorer. Anytime now, you'll see a play bar at the bottom and the total length of time, so you don't have to get into the animation suite. So let me give you an example of that. I'm going to make myself a cut plot here, very similar to how I monitored the solve. And let's watch mass fraction of water, volume fraction of water. Those are the things I turned on in the calculation control. I might use about 100 different colors on the gradient to take a look at it. I can preview it and make sure it looks the way I want. And the nice thing about having that Transient Explorer turned on is that I can simply come down and hit a play button and watch this play without having to deal with any animation keyframes. So it looks like I'm getting the behavior I want. I would say after these, it's not a bad idea to exit the Transient Explorer and look through the rest of these for flow trajectories. If you've made goal plots, here's where you can get the hard numbers and hard values out of those. So that's a very quick example here of this dam breaking problem and using free surface. Overall, it's not a very difficult thing to do to simply check on the free surface box and set up any condition you need. But in this case, I wanted to dive into a few advanced techniques that really help the setup. Initial conditions can be set for just about anything. In this case, I wanted to say just one volume here is water while everything else is air. So I used the feature of FlowSim called initial conditions. The other thing I got into was the calculation control options. And that's right-clicking on the input data folder. You can find those. There you can set up your time step, your saving options, your finishing condition. That's where you could turn on solution adaptive mesh refinement. So those are those deep down controls. And while I was in the calculation control options, I specified what parameters I wanted to be available for the Transient Explorer. This way I didn't have to save multiple time steps and work in an animation suite. I could simply plot any one of those results and I'd have a play button right on the screen. So I know that's a little fast, a little in-depth, but I hope it gives you an idea of what can be done with free surface and really how easy it is to set up compared to other simulation types. So that was 2D. I chose a 2D transient study like that because I knew I would be able to solve it quickly in today's webinar and give you an idea of how to monitor those solves in real time. Let's take a look at something a little bit in depth that would take a longer solve time, and that would be a larger 3D free surface simulation. And to do that, I want you to head over to our YouTube channel. We have an easy YouTube channel to get to, youtube.com. The username is MLC CAD Systems. Very easy to find. We have a ton of great videos there. It's really where you'll find all of our videos, from installation help, whether it's Mastercam or 3D printing and SolidWorks. But head over there and check out a video I did on free surface. In this case, I wanted to check out in-depth tank sloshing. And that's a tanker truck idea on a highway. How do we deal with baffle plates? How do we drive these large tanker trucks around while still getting stability on the road? I use this to compare multiple designs together to analyze some baffle plates inside of a truck like this. Of course, it makes great animations, but it allows you to really do configuration-specific design comparison side by side. The setup is very similar, but I wanted to make sure that today we looked at some of these behind-the-scenes techniques that I'm not going to be able to dive into in a shorter video like that, such as setting up your initial conditions, getting deep into those calculation control options, and using that Transient Explorer for very easy post-processed animations. So from here, I know you've probably got some questions. What's next? Go check out the free surface YouTube video. The next place to stop is our main website, mlc-cad.com. That's our main site where you can find event calendars, public training calendars, and tech support information for all things SolidWorks, 3D printing, or Mastercam related. Of course, you can always call or email. If you're not at the website, just call our 800 number for SolidWorks tech support. That's 800-364-1652. option 2. So if you're a subscription holder of a SOLIDWORKS seat, you can call that number or shoot us an email at solidworksupport@mlc-cad.com. Myself or one of my colleagues or another simulation expert will always be there, happy to answer questions.